Good afternoon. Welcome back to our online seminar series, Machine Learning Needs Mathematical Optimization. We have the pleasure of having today Thibaut Vidal. He is a professor at the École Polytechnique de Montréal in Canada. He has a joint PhD also from Montreal and from Troyes. He has been working a lot on vehicle routing problems and other combinatorial problems. He has also done extensive work on heuristic search and more recently he has been involved in machine learning too. He has received a number of prizes for his research, so I'm just mentioning a couple of those. So he has a Verilog dissertation award, and this is awarded by the Euro Working Group on Vehicle Routing Problem and Logistic Optimization. He is also recipient of awards from the Transportation Science and Logistics section from Informs, and he also has a Best Paper Award from the journal EJOR in the category of theory and methodology. So Thibaut has a chair, like you can see in the slides, a chair in data-driven supply chains, and moved recently to take that position at Montreal. So we are very pleased of having you today, and the floor is yours.
And thank you so much, Dolores, and thank you for everyone who is involved in organizing these seminars. It's a very super interesting seminar series, and it has been always a great pleasure to see the talks. And now I'm very happy to be here and participate to this. So I'm going today to talk about machine learning on explanation methods, and more specifically the task of counterfactual explanations in tree ensembles. If there is a bit more time, depending on how fast we go, we may review one additional small topic very quickly, but this is focused on counterfactual explanations. So we have seen a growing number of applications of machine learning in a very large number of contexts. So contexts such as like recommendation systems, when you are going to see the next video on YouTube, or computer vision, when you want to have like some small task important for recognizing some objects, text edition and translations. These are use case in which we have already been using actually machine learning for many, many years. And today we see a shift in the range of applications towards applications that are even more critical. Like we have seen a lot of COVID applications of machine learning. We have seen application in medicine, for credit evaluations, in the criminal justice system, something that is a bit discutable, whether we should be using machine learning in such context. So when you start to be in applications where a machine learning decision can make the difference between life or death, or freedom, or staying in jail, we are talking about very critical applications. And this is a recent trend of using machine learning for very critical applications. And it is something that is, in a sense, worrisome, because many machine learning techniques are not yet fully ready to be deployed in such environments. Explanations and interpretation methods are needed to avoid a very big pitfall in those areas. So in particular, the kind of very important pitfall and questions that arise in such application is how to ensure fairness in machine learning systems, how to avoid any kind of prejudice or bias. And biases, they come in many shapes and forms. They can come from gender, they can come from age, from racial grounds, and just kind of excluding sensitive information from data sets. It is often not a meaningful way to just avoid these biases, because very often, for example, social and economical backgrounds are related to many other factors. And even if you don't use gender or race, for example, in a model, you could very well use other features that are heavily correlated and somehow use a proxy of these variables. So there's been a huge discussion about how to avoid biases, how to protect sensitive attributes in machine learning, and how to ensure that those systems are fair and also reliable. So this work is part of a general effort of trying to provide more explanations and giving tools to better understand how the decisions are made and how to change the decision possibly. We are going to talk about this. There is two important notions that have been often around in the machine learning literature. There is the notion of explainability and the notion of interpretability. And they are a bit quite different. So we had a talk, for example, of Cynthia Rudin, who works a lot in this area. And the common convention is that when we come and talk about interpretability in a model, we are looking at a model that can be understood by design. For example, if I have a rule list, like I can follow each condition, follow how these conditions are respected or not respected by my data, and fully understand the path of the data into the classification process. This is something that could be transparent and understandable by a human. So that means that we have access to the internal process of the machine learning model. When we talk about explainability, we are looking at a model that is not necessarily transparent. So it could be a black box. It has some components that are not fully understood by everyone, perhaps for security reasons. And the explanation method would be, in that case, an additional algorithm that is put on top of the machine learning models in order to explain part of its decisions. So very often when we talk of explainability, we are talking of actually of two layers of algorithms. Perhaps a black box algorithm or something fairly complex, and an explanation method that is on top. Obviously, if you want a fully transparent and intelligible decision process, it's very likely that interpretable methods are more useful and transparent for the users. Whether explainable methods based on two algorithms, they could go wrong in two ways. They could go wrong because of the subjacent model, and they could also go wrong because the explanation method is not doing a proper job. So if there is a bug or something that is not understood, it would come from both sides, whether the explanation perhaps is not accurate or whether the model has something wrong inside. So I'm just going to discuss, for the sake of completeness, a few explanations on interpretation methods today. So just to establish the notations, we are looking at a data set which has some data points characterized by some features, which are the xi, and we have classes or targets, which are yi. We assume that these samples, the pairs x and y, they come from a known distribution. And our goal in supervised learning is to learn a predictor function that associates a class to each sample in X. So there is a very large number of methods that have been designed in machine learning. It goes from very simple models like linear regression or logistic regression to support vector machine, for example, where you can you draw a hyperplane in order to best separate the points if possible. You can go towards rule lists on decision trees, which are a bit more complex structures, but which are basically rules that you follow in order to arrive to final classification. We are going to come back on decision trees a bit later because this is going to be a very big element of our talk. And then, well, these methods, they are usually fairly simple to explain. They are based on few parameters. So you can look at those parameters. You can easily make specialized feature importance measures based on that. And you can generally understand what is going on. However, in terms of classification, accuracy, or overall performance and flexibility, these are not always the best methods possible. In recent years, we have seen a big trend towards much more complex models for learning. For example, based on ensembles of those basic learning algorithms. For example, joining together many decision trees to make a forest, and then the majority of the forest will take the decision. We have seen deep neural networks, which are growing and becoming huge and extremely complex. And even in the literature about AutoML, it is very common to kind of hybridize different models together to make a hierarchy of methods that basically takes decision and that is automatically trained. So we end up with very, very complex machine learning models where we cannot easily just say, well, this thing happened because of that. So ensembles of tree is going to be a very big focus in this talk. When we talk about explanation methods, we talk of different flavors of methods, actually. The first is, well, a decision has been taken. I'm not looking at the specific data point, but I'm maybe looking at what are the features that were important for that decision. So there has been a number of studies about how to associate some importance measure to features. So the features are the different dimension of the data that is provided to us. One way of measuring the importance of a feature is just removing all the information related to this feature. Usually this is done by shuffling the features between different data points used for training, and then seeing how much the prediction accuracy of the model degrades. If the prediction accuracy degrades a lot, then we would say that this feature is important. That's what is called permutation feature importance. We just shuffle this feature. If it's important, it should impact a lot the result. There is a number of questions related to how to do that, whether, for example, you should retrain or not the model after doing the permutation. And this will lead to different variants of permutation feature importance. Another very classical method for feature importance is the use of Shapley values. So Shapley values, they come from an analogy between basically the task of classifying and game theory. And it's basically assuming that each player is a feature and that the prediction is the surplus. So there is a formula to calculate the Shapley values and to estimate it. And this is going to give you some feature importance measure based on a game theory analogy. The issue with this is that, for example, if you have two features that are very heavily correlated or identical, then the contribution of these features tends to be distributed between the features that are correlated. So you may have a feature that's quite important, but because it's correlated heavily with like two other copies of itself, then it will look less important in a Shapley value-based estimation of feature importance. Then we have things that are not really about feature importance, but more about making models a bit more transparent. So a very big trend and over the years has been to kind of imitate a model with another. So suppose I give you a very deep neural network that is very, very deep and that is difficult to store, difficult to use. You may be interested in taking this deep neural network and create a smaller network that reproduces most of the behavior of that network. This process is called teacher-learner. One of the network is the teacher, the other is the learner. And this can be used, for example, for compression of model, trying to have something more compact that is faster to use, easier to store. And it can be also used for interpretation. For example, I will be interested in having a smaller deep neural network or a different model even that does more or less the same as a complex mechanism, because then I can more easily explain what this learned surrogate model is doing. In particular, over the last year, I've been already doing a number of talks talking about born-again tree ensembles, which was a technique to transform a random forest, which is a fairly complex model because it has many trees, into a single tree that has the same prediction function. This was done with mathematical programming techniques and permits a better interpretability. But this is not the subject of today. We are going to talk of something else. We have also other models that are not designed to be like a global retraining or summary of the model, but something much more local. So a very famous method in this domain is the method that's called LIME. It's local interpretable model agnostic explanations. So the idea is that I give you a certain data point or a place of the filter space where I want to get an interpretation. And I generate data around this data point and pass it through the model. Then I look at this data and I put some weights based on the distance from the point of origin. And finally, I train something that is interpretable on it, like some regression algorithm. And I use it to tell, well, around this data point, according to a regression, this is what the model is doing. It goes, it has these coefficients, or for example, this is the decision frontier stated to it. You can basically take a local look and train some surrogate model locally to try to explain what is going on. Final explanation technique, which has become very important recently, is called counterfactual explanations. So suppose you ask for a credit and you go to the bank and you say, well, I would like a credit of that amount, and I would like it to be like 10 years, and I have these revenue conditions, and I have this job, this is my background. And the bank tell you, well, sorry, but we cannot give you a credit with your data. It's not awarded. So the first reaction that you would do if you were facing a human would be to say, well, what can I do? You are refusing this credit. Should I take it for a longer period? Should I take a smaller amount? Please guide me to have perhaps success in the next application if I change a bit my data. And that's exactly what is the purpose of a counterfactual explanation. So a counterfactual explanation is a response to this question. It is a new data point that is close to the origin point and that permits to shift the classification outcome. So it's something that tells you, well, you have asked 40,000. This is your origin point. If you were to ask 30,000 and give like 3 more months to reimburse, then it would work. So basically, there are 2 changes to the data that you need to do. Like you need to ask less and extend the duration, and it gives you a new data point that gives a positive outcome for the classification. Like, oh, you will be a good creditor. So that's it. That's basically a simple answer. The thing is, depending on the prediction function, fx, so we are looking at minimizing the distance between the origin point, which is the x hat, and what we call the counterfactual explanation x. And we want the outcome of the prediction on x to be the desired class C star. Okay. It doesn't look like something difficult. I mean, it's just searching in the vicinity of a point, an outcome, a data point in such a way that the outcome is the desired outcome. The big issue is, in many cases, the prediction function f can be something fairly complex. If we are looking at very simple models, which are like convex and differentiable, perhaps there will be some nice property that allow you to search with some kind of gradient descent or some local method and guarantee to find something good as an explanation. But if you have a very complex ensemble, tree ensemble, or a deep neural network, searching for such a point in the vicinity that returns the right outcome is something that can be a fairly hard optimization problem. So we are going to study it in this talk. So we are going to take a focus on one specific type of model, which is tree ensembles. So tree ensembles, they are basically several decision trees. I'm just going to zoom a little. This could be an example of tree ensemble that has been already trained. So I'm kind of looking at a medicine application for examining whether I think some sample is cancerous or not. And the first three will analyze one specific feature. And if this feature is smaller than the threshold, it goes on the left, otherwise goes on the right. And when we pass data into each tree, it will return to us a classification. Many trees. Like here, I just written 5 because my slide is small, but it's very typical to use hundreds of trees. And when we look at the outcome of such a classifier, it's very typical to take the majority vote of the trees. So the class that is the most represented in the leaves is going to be the output of the prediction function. So let's reframe, just illustrate what is counterfactual search in this context. So I have given a data point. This data point has taken specific paths in each of the trees. And unfortunately, my outcome, the class that I wanted, was not the majority class. For example, my credit has been refused because the majority of the trees decided to refuse this credit. So actually, when I want to look for a course, a counterfactual explanation, I'm looking for a data point that would be fairly similar to my first data that I had, but that will take a different path in some of the trees in such a way that the majority shifts in my favor. Okay. We are going to frame this as an optimization problem. And it's actually not a very nice problem. It is very combinatorial because there is many trees and the decision function, they are like stepwise functions and nonlinear. And actually, when we look at the decision function of such a method, such a model, it has a number of pieces that is the product of the number of leaves of the trees. So if you have like 100 trees and each tree has 2 leaves only, there could actually be an exponential number of pieces in the prediction function, like 2 power 100. The second issue is that if you decide, for example, to change one of the figure, like the amount that you want to borrow, like 30,000 instead of 40,000, some of the trajectories of the tree are going to change. Perhaps they will shift from 0 to 1, but other of them may change from 1 to 0. So it has a global impact. If you change something, it changes the trajectories in all the trees. And finally, you cannot just differentiate and make it smooth and nice. It is something that for us, like optimization person that have some knowledge of combinatorial optimization as well, it's really, really in our, I would say, in our park. This is the kind of game that we like. It's very heavily combinatorial actually. So we have surveyed the literature recently. So up to, let's say, last year or early this year, where we did this literature review, most of the algorithms were based on heuristics. So one very classic method is called feature tweaking. So it basically tried to look at every possible way to take a different path in each of these trees, see which feature needs to be changed, and it will enumerate these possibilities. Since there is a number of leaves that can kind of enumerate in most cases, this is a finite process, and these can be considered as a heuristic to try to solve the problem. Unfortunately, it's not something optimum because one path of a single tree not always characterize the best action that lead to a good counterfactual explanation. And in our experiment, we even realized that sometimes the best counterfactual explanation that this method found was like 30 times more distant from the origin point than the optimal explanation that we could generate with an optimal search method. The other thing is, when we talk of heuristic, we inevitably talk of mistakes. So I have said the mistake can be like up to multiplied by 30 times, like 3,000% mistake. In other cases, it may be just 10%. This totally depends on the data point. So you may wonder if it is really a fair way of proceeding to use a heuristic that is very unstable on different data points. Some sometimes have good answers, some have bad answers. I'm not thinking that is a very fair way of treating different subject on subject groups. And perhaps due to the specificity of some subcategories of person or data point, you may even have a performance that is dependent on the subcategories. So I'm not really convinced that a heuristic search of counterfactual explanations is a very transparent and fair process, because there is a lot of exogenous factors that come up due to the type of search method that you are using. So when we saw that, we directed ourselves towards something that would be more systematic. And as machine learning and also mixed integer programming practitioners, a good model and technique to search for counterfactual explanations appear to be mixed integer programming based. So we are going to model the behavior of a random forest, a tree ensemble, as a mixed integer programming model, and see whether it's actually possible using MILP to find good counterfactual explanations. A small parenthesis, I have seen that a recent talk also in the NeEDS project from Dolores has taken a similar path, and I encourage you to look at both talks also to make some connections. So let's look at this. So how to model this as a MILP? We are going to represent the problem of the decision function of the tree ensemble as a set of linear equations. And some of the variables of this equation are going to be integer variables. Our model, as you will see, it has some good characteristics. It has a logarithmic number of variables as a function of the data size, and it has a very tight linear relaxation. The other thing is that because mixed integer programming is very flexible, we'll be able to adapt it to a very large number of contexts and requirements, which are important in such applications. So the first thing you want to do is to model how your data point flows through the different decision trees. So I have illustrated a very small decision tree here on the left. For example, it could be like the first test is on the second feature, and if it's 0.5, it goes on the left, otherwise it goes on the right, and then the next test is on the first feature. If it's smaller than 0.4, it goes left, otherwise right. The idea is that you will basically associate a y variable to each node, and it will be valued 1 if the current data, the current counterfactual explanation, flows through this test. Okay, and as it's a flow, we are going to set up some flow conservation constraints, which are very typical in such things. And then we need to connect these flows with the decision of branching, which is whether it goes left or right at each node. So at each level of the tree, we create a lambda variable that will take value 0 if it goes on the left and value 1 if it goes to the right. And those branching decisions, left or right, there is a single one for each layer of the decision trees. They are going to be kind of the only binary variables of our model. Okay, we can prove actually that we can connect the branching decision about left and right with the flows through these two equations in such a way that the flow variables, they remain integer as well. On these variables, we are going to do that for every decision tree. But of course, if we stop there, the decisions that are done in each tree, they are kind of disconnected. They are not related to each other. It would not guarantee us that there exist feature values that can be consistent with those branching decisions collectively in the entire forest. So for that, we need to make an additional connection with the real values of the features of the counterfactual explanation. So we do that by creating for every feature a set of variables that are the mu variable, which are actually what we call an order simplex. the first variable mu0 will start to fill up and get some value. When it's totally full, then the next variable can fill up. And when it's totally full, the next variable can fill up. And basically, when it fills up from here to here, that means that we are going with the feeder value from the 0 to threshold 0.4. And then the next variable fills up, and that means that we are going from 0.4 to 0.6 and 0.6 to 1. Okay. And there is a very nice way to connect these variables that permit us to express what are the values of the features with the branching decisions. Because the branching decision, they tell you, you go left and you have the threshold 0.4. So if you go left and you have a threshold 0.4, that means that you can have some value in the mu0 variable, but you cannot have any value in those other variables. So there is a very simple relation between the mu variable and the y variable that just is a constraint that involves one variable of each. Okay, it's a very, very sparse constraint, and it directly links how these two sets of variables behave. There is one thing that is nice, is that when we work with continuous features, you don't need to use any other integer variable to do that. You can leave the mu variable to be fully continuous, and the MILP just has to care about this lambda variable. Everything else is continuous, which is very nice. And the second good property of this model is that all the equations that are here, which are the more numerous, they just involve two terms. So they are very sparse. You look at the total number of terms in the model, it's like a huge matrix with most zeros. There is very, very few non-zero entries in this model. Okay. There is ways to adapt this model to many other types of features. I'm not going to spend a lot of time on this because I'm already talking a lot, but you can easily adapt this model to deal with categorical features, with features that are ordinal, which is like, for example, customer satisfaction, low, medium, high. Well, there is an order in the feature levels, but there is no meaning of an intermediate value. Like if it's between low and medium, it cannot be like 0.5 low and 0.5 medium. You have to be in one or the other. So you can also model this in our model. And you can also work with binary features. You can model the objective function. So as I told you, the usual goal is to search for an explanation that is in the vicinity of the original point. So you want a distance to be minimized between the initial state of the person who asks for credit and the explanation that we give to this person. So it can be either a L0 norm, which would be telling, well, try to find an explanation which has to modify the smallest number of features. That would be the L0 norm. And that requires a few extra binary variables, of course. You can go with the L1 norm, which is a weighted objective function that measures the change of every feature that is needed and put a weight on that. You can go with L2. Actually, you can go with a lot of different objective functions in our model. That's totally doable. And finally, we have to make sure that we achieve the majority vote. So to know whether we achieve or not the majority vote, we need to know if the flow arrived to one class or the other and kind of sum everything. And we want the class C star to have a larger number of flow that is arriving there than the other classes. And that completes our model. We have everything with this. So it's very nice to work with mathematical programming because what I've described to you was something fairly simplified. I said, well, we have an objective function, it's a distance. We look for a counterfactual explanation that is close to my original point, but I did not give much other constraints. In practice, there could be a lot of other constraints. For example, some features are impossible to change, like my gender. I'm not going to change that for a credit. My age is something that's going to be always increasing. So this kind of constraint in a mathematical programming context, it's straightforward to put just with an additional constraint. If I was with a heuristic, perhaps something monotonic would not be so easy to implement. I would have to modify my method. But since we are working with mixed integer programming, it's fairly easy. If I know also linear relations between features, for example, I know that two features that are heavily correlated, so I cannot just chain one without chaining a lot the other, and that I'm able to characterize this relation through linear relations. I can easily put that as additional linear constraint. And that's just going to impact, for example, the simplex algorithm that is running in the background, not going to be a very heavy impact on my methodology. If I have known logical implications between features, for example, some feature being true implies that the other is true, the same. I can easily set that in the mixed integer programming context. Okay. Even if I have resource constraints like time, like changing some features would take time, and I have a certain time budget available. Well, no problem. This can also be modeled in MILP. If I had to do that in a heuristic again, it would be very, very challenging. Okay. I've seen a hand being rising. Would you like to ask something very quick?
Yes, so Emmanuel has a question.
Yes.
So I think Christina
Yes.
is
Hello.
giving.
Hello, and thank you. Sorry for interrupting you, but this is exactly referring to the last line of this slide. So this you mentioned that you can add linear constraints. I agree. But how about nonlinear expressions for these resource constraints? Well, think of goodness of, for instance, you can require some minimal goodness of fit for your model or something like this. So this takes us easily out of the linear domain, and what happens then?
Yes, indeed. So there is a lot of things you can do with a linear model, with linear constraints on equations. And a lot of things can also be done by using discretizations. So when you have nonlinear expression, sometimes one way to work around with this is to have a discrete representation. And then with this discretization, you are able to come up in a more linear world. But this is really like case per case study that needs to be done in such a context. So indeed, when we start to be nonlinear, things are much harder for MILP. And that's why, for example, the first subject of study that we did in this work was to look at tree ensembles, because they behave linearly. If you look at a neural network with general kind of neural networks, you have much more nonlinear behaviors. And it's very, very difficult to do the same work, for example, for a neural network. It would not work very well.
Thank you.
It has a lot of power within a specific framework, which is when you can express things with linear relationships. I will briefly look at the data, the experimental data that we have. So the first thing we wanted to know is whether we can apply such a counterfactual explanation based on mixed integer programming at scale. So we took a number of data sets, which are actually fairly large, some of them. Like we have some data set that have up to 57 features and a number of data points that is here. And this is the number of numerical, binary, and categorical features. They all come from the UCI data set or from ProPublica in the case of Compass. And what we did was to create a random forest with 100 trees on the depth of 5. And every time we took 20 samples to look for a counterfactual explanation. And we measured how fast it is to find such an explanation. The good surprise was that in most of the case, you get counterfactual explanation that are done in the order of a fraction of a second or a seconds. So the largest time we got was around 10 seconds. And the smallest time we get is usually a small fraction of seconds. So it is possible to obtain reliably fast counterfactual explanations for with the considered mathematical model on those 8 data sets, which are really non-trivial. we compared with the different techniques. There has been a paper that has been also designing a mixed integer programming model for counterfactual explanations, and which works for 3 ensembles. It's called the OAE method, and it has been initially presented in a paper number 8 and then extended with other distance metrics on another paper. And it has a performance that is quite nice on some data sets, but we have seen that on very large data sets, sometimes it just fails to find a counterfactual explanation in a reasonable time. It takes we let it run for 5 hours on some data, and it did not complete. So that was a bit less scalable on the larger scales. On MACE is another technique that is not based on mixed integer programming. Actually, they use, if I remember well, a susceptibility solver to try to find a similar explanation. And it finds optimal or near optimal explanations for all the medium-sized data set. But again, for the large scale, it would just run on not terminate. The last thing that is interesting is the feature tweaking. I told you, feature tweaking is reasonably fast, but not so fast actually compared to the others, but quite stable in terms of time. But it doesn't have a very good quality of explanation. Very often the explanation, they will overshoot what is needed to do. So if it's possible to run something optimal, it's usually a better solution. The last thing that can happen is that even the feature tweaking may not always find a feasible counterfactual explanation. It doesn't always happen actually that there is an explanation at the end of the process. This is how the time grows with the depth of the trees and with the number of trees. So the black is the mathematical programming method that we propose. So it scales up pretty well actually, even when you have 256 leaves in the trees, which is not so small. 100 trees with 256 leaves, that's 25,600 leaves. So all the combinations and everything, that makes a fairly hard problem. And this is with the number of trees. We can still scale up in terms of trees as well. The last thing I wanted to discuss is about plausibility. Sometimes when you look at counterfactual explanations, you have explanations that are kind of mere artifacts of the prediction function. For example, I like to show this example, which is the binary classification problem. And there is the blue region here, more or less, and there is the red region that is here, more or less. If you start from the yellow point that is here, on that you put no constraint on plausibility, an optimal counterfactual explanation would be just here. Why it's here? Well, it's because now the majority is red in this place and is very nearby. So, well, it would look like a good explanation. But for all of us, this explanation doesn't look like meaningful or plausible for a good reason. All the points that are red points, they are here on this region. There is no red point here. The prediction function is red here just as a kind of artifact of the random forest, but there is no actual data points in this region. So probably this is not a region that even exists, a combination of features that are probably implausible. So you may wonder how you could force the counterfactual explanation method to find an explanation that is in a region that is plausible enough when you look at the data. And there is a technique that is called isolation forest that has been originally designed to find outliers in data. The isolation forest just consists of training random trees. You create a lot of random trees, and due to the way you create the random trees, you realize that outliers, they tend to have to be classified in the random tree at a level that is less deep than points that are in the core of the distribution. It makes sense because if you need to separate an outlier, a few tests usually are enough. But if you need to separate a data point from the rest of the data, you need much more separation to do that. So you can create an isolation forest that returns a threshold about whether or not a point is or not an outlier. And because it's a forest, you can actually use exactly the same model to model it within a MILP and set this as a constraint to impose that the explanation that you find is considered to be plausible from an isolation forest point of view. And that doesn't change much to the performance of the model. This stays fast in all cases. So I'm going to conclude. We can do optimum counterfactual explanation for many data sets of practical interest. Using mixed integer programming is interesting because as long as we are within a linear context, and in some other cases, we can model a lot of objectives, kind of penalty terms and constraints that relate to two kind of things. Actionability, like can I move some specific features, linear correlations, and also plausibility. And when we know that models are evolving fast, so it's useful that we can customize models like this and add some constraint as needed in order without redefining an entire heuristic, for example. And for future works, I recommend to focus on improving performance, perhaps improving the models and the solution methods, but still keeping an eye on formulation ease and flexibility. Let me just show you one last thing. I will thank you for your attention. You can easily contact me on my email at thibaut.vidal@polymontreal.ca. You can look my website, and the source code of this project is on GitHub under my username. And we really strive to make all the source code of all our papers available on this page. You can also check on Twitter. I usually announce when there is new works. And I would like to gather your attention on a specific event which is currently ongoing, which is the DIMAX challenge. So I'm part of the organization team, and this challenge aims at solving better vehicle routing problems. There is already a number of teams that are registered. We have a lot of people coming from the traditional operation research community. But since there has been a very growing interest in solving vehicle routing problems with the classical combinatorial optimization problem through machine learning, I strongly encourage other teams that don't necessarily come from NOAA background to join in and also propose some solution methods, because the comparison will be very interesting with teams that come from very different backgrounds. So I have the references. I can send it to Dolores or put it on my website for further consultation. And I'm available for questions. Thank you so much.
Thank you very much for the very nice presentations. So now we open the floor for questions from the audience. So as usual, please raise your hand, and then we will give you a voice and the possibility of sharing your camera. So we have Ilker with a question for you, and we are going to give voice to Ilker.
Hi, I hope you hear me well.
Yes, we do hear you well. Thank you.
Excellent, excellent. Thanks for the organization, and thank you very much for the nice talk. My question is about what happens when the data changes a little bit. Because now you're trying to come up with these counterfactuals, which I find a very good idea and very inspiring. But of course, the data changes, and if a little bit data is included in the data that we have already trained on, the counterfactual can also change. And then, of course, the explanation changes. And have you ever considered this? Because this is one thing that I am also facing quite a bit, because I'm trying to come up with these interpretable rules. But if the data changes, of course, the rules also change. Do you also see such a problem in your case?
Yes, definitely. So you spoiled the next work that we are working on. We have been considering already for a number of months the question of robustness in counterfactual explanations, and especially robustness, for example, even to retraining. Because when you look at counterfactual explanations in the current state, they assume that the model is trained on that nothing will change, no weight will change, and so on. But it's not true that when you give someone a recourse, well, it's going to change whatever is profiled and ask for more time and so on, it may come back in 1 month, and the data may be different, the model may be retrained, and it could end up that if you have not considered such a thing, the explanation that you gave is not valid anymore. So I think that in the coming years, we need to evolve further from simple explanation for fully trained model to explanations that are robust to retraining and robust to kind of data changes. And that's probably the next step that we're going to see.
Excellent. So apparently we are really trying similar things. I'm on the rules part and you're trying with the counterfactuals. Thanks. This robustness is indeed very interesting. Maybe we'll also meet offline. Thank you. Thank you for the talk again.
We should keep in touch. Just drop me an email and I would be happy to do some brainstorming about that.
Yeah, let's do that. Okay. Thanks a lot again. Bye-bye.
Thank you very much, Ilke, for your presentation. Yes, so any other questions from the audience? I'm looking at the chat, and the chat is about saying thank you. So no questions there. Is there any other question from the audience? Yeah, I think there are no other questions. It has been very nice to see another way of solving counterfactuals in 3 ensembles. So thank you very much. And I think we will stop here and say thank you for your presentation again, and say to the audience that next Monday people will be perhaps, at the Infos conference. We have decided not to have a clash with the Infos conference, and we will be back at the beginning of November with new talks, and the next speaker will be Andrea Lodi. So we hope to see you back in 2 weeks. Thank you so much to the audience for all these pleasing comments.
Okay, excellent. Thank you for the invitation, and I wish you a great day.
Thank you so much.
Thank you, Thibaut.